Okay, so today is second targeted cram session. We're going to talk about encryption. Okay, and just a quick, quick look at the schedule coming up. Today is the 8th, and we have today and then Friday amongst the odd period. And then that's it. I don't see you again until after the test. Okay. For those of you who are deciding whether or not they want to pass the class, the last day to submit anything for April assignments is that same day. But if you're taking the test, you probably have everything done already. Otherwise, you probably wouldn't be taking the test. Okay, so we are going to continue with the encryption portion, starting with the course vocabulary document down here on the 19th, just holding a space. And then we'll do some practice questions from the, whatever it's called, all three practice tests. And I think these are, no, that's all the tests. That's the 2020 answers, and that is the 20. Okay, so the topic of encryption is making secret messages. Okay, we've all done this as kids, where it seems almost intuitive that the whole idea of a substitution cipher, where you have like every letter means a different letter, and you and your friends can write messages and then unscramble it to pass a secret message. Okay. The majority of history is that type of thing. Symmetric key encryption, also single key encryption. It is two people that use the same key, as it's called, to encrypt a message or, scramble up a message. And the same key, they both use the same key to decrypt or unscramble the secret message. Okay, that works fine as long as the two keys are kept secret, or the one key, the shared key, is kept secret. With also but the negative is the two people or the two parties, whoever, need to meet in person first to exchange the key. Because the reason why, contextually, you don't trust the message system with the potential of somebody intercepting your secret message, or your message in general. That's why you're using encryption. That means you don't trust that same method of sharing the key. Okay, so it needs to be done in person. You go your separate ways, and then the secret key will work. That doesn't work for the internet. The internet needs a way to encrypt messages without ever meeting the person. And the way they do it is with a system called public key encryption, or asymmetric encryption. And we'll see some details about that. But it allows you to send essentially half of the key to somebody. And send it means anybody can see it. The person encrypting the message uses that public key to scramble up their message, but only the private key of the receiver can unscramble it. So as long as that private key is not shared, the message can be transmitted, scrambled, and nobody can unscramble it. Okay, it's called public key encryption, but it's also two-key, multi-key encryption, or asymmetric encryption. There is a private key, but it works combined with a matching public key. And the takeaways, the keys, are that it's 2 keys. This is the part of the question on the test you will see. Something about multiple key or asymmetric. Asymmetric meaning the 2 parties have different keys. You have your public and private key. I have my public and private key. I scramble up the message I want to send to you using your public key, which can only be undone with your private key. So it's not, you're not sharing the same encryption and decryption. That's what. Yes, it is. It's how the internet works. We couldn't do any sort of banking or commerce or anything on the internet, anything that needed to be secured without it. There are a couple of algorithms that solve that. And we'll see a couple of, well-produced YouTube videos that explain it. But as far as getting questions right, this is a unit that we're going to spend more time on and learn things about. But to get the questions right on the test, you need to know that public key encryption, also known as asymmetric or multi-key. I should put that in here. Asymmetric is 2 M's apparently. Asymmetric, 2 keys. Okay, and let's watch a couple of short-ish videos. There is Simply Explain, which is actually more complex. Let's watch the crash course one. Like I said, we're just going to watch it on the, let's see how the lag is. Oh, it's bad. Okay, so the video that is not going to be played on the replay of this meeting is called, well, the first one is Encryption Crash Course. And we're going to watch it on the front screen. Okay, so let's go like this. And like that. And I should have loaded this. It's called, where are we? Encryption Crash Course. I think we've watched videos from this organization before, or this series before. All right, here we go.
I'm Carrie-Anne, and welcome to Crash Course Computer Science.
Cryptography.
Over the past 2 episodes, we've talked a lot about computer security. But the fact is, there's no such thing as a perfectly 100% secure computer system. There will always be bugs, and security experts know that. So system architects employ a strategy called defensive depth, which uses many layers of varying security mechanisms to frustrate attackers. It's a bit like how castles were designed. First, you've got to dodge the archers, then cross the moat, scale the walls, avoid the hot oil, get over the ramparts, and defeat the guards before you get to the throne room. But in this case, we're talking about one of the most common forms of computer security, cryptography. The word cryptography comes from the roots crypto and graphy, roughly translating to secret writing. In order to make information secret, you use a cipher, an algorithm that converts plain text into ciphertext, which is gibberish unless you have a key that lets you undo the cipher. The process of making text secret is called encryption, and the reverse process is called decryption. Ciphers have been used long before computers showed up. Julius Caesar used what's now called a Caesar cipher to encrypt private correspondence. He would shift the letters in a message forward by 3 places. So A became D, and the word Brutus became this. To decipher the message, recipients had to know both the algorithm and the number to shift by, which acted as the key. The Caesar cipher is one example of a larger class of techniques called substitution ciphers. These replace every letter in a message with something else according to a translation. A big drawback of basic substitution ciphers is that letter frequencies are preserved. For example, E is the most common letter in English. So if your cipher translates E to an X, then X will show up the most frequently in the ciphertext. A skilled cryptanalyst can work backwards from these kinds of statistics to figure out the message. It was the breaking of a substitution cipher that led to the execution of Mary Queen of Scots in 1587, plotting to kill Queen Elizabeth. Another fundamental class of techniques are permutation ciphers. Let's look at a simple example called a common mass transposition cipher. Here we take a message and fill the letters into a grid. In this case, we've chosen 5 by 5. To encrypt our message, we read out the characters in a different order. Let's say from the bottom left working upwards, 1 column at a time. The new letter ordering, what's called a permutation, is the encrypted message. The ordering direction, as well as the 5 by 5 grid size, serves as the key. Like before, if the cipher and key are known, a recipient can reverse the process to reveal the original message. By the 1900s, cryptography was mechanized in the form of encryption machines. The most famous was the German Enigma, used by the Nazis to encrypt their wartime communications. As we discussed back in episode 15, the Enigma was a typewriter-like machine with a keyboard and lab board, both showing the full alphabet. Above that, there was a series of configurable rotors that were the key to the Enigma's encryption capability. First, let's look at just one rotor. One side had electrical contacts for all 26 letters. These connected to the other side of the rotor using cross-crossing wires that swapped one letter for another. If H went in, K might come out the other side. If K went in, F might come out, and so on. The letter swapping behavior should sound familiar. It's a substitution cipher, but the Enigma was more sophisticated because it used 3 or more rotors in a row, each feeding into the next. Rotors could also be rotated to one of 26 possible starting positions, and they could be inserted in different orders, providing a lot of different substitution mappings. Following the rotors was a special circuit called a reflector. Instead of passing the signal onto another rotor, it connected every pin to another and sent the electrical signal back through the rotors. Finally, there was a plug board at the front of the machine that allowed letters coming from the keyboard to be optionally swapped, adding another level of complexity. With our simplified circuit, let's encrypt a letter on this example Enigma configuration. If we press the H key, electricity flows through the plug board, then the rotors, hits the reflector, comes back through the rotors and plug board, and illuminates the letter L on the lab board. So H is encrypted to L. Note that the circuit can flow both ways. So if we type the letter L, H would light up. In other words, it's the same process for encrypting and decrypting. You just have to make sure the sending and receiving machines have the same initial configuration. If you look carefully at this circuit, you'll notice it's impossible for a letter to be encrypted as itself, which turned out to be a fatal cryptographic weakness. Finally, to prevent the Enigma from being a simple substitution cipher, every single time a letter was entered, the rotors advanced by 1 spot, sort of like an odometer in a car. So if you entered the text AAA, it might come out as BBK, where the substitution mapping changed with every key press. The Enigma was a tough cookie to crack for sure, but as we discussed in episode 15, Alan Turing and his colleagues at Bletchley Park were able to break Enigma codes and largely automate the process. But with the advent of computers, cryptography moved from hardware into software. One of the earliest software ciphers to become widespread was the data encryption standard developed by IBM and the NSA in 1977. DES, as it was known, originally used binary keys that were 56 bits long, which means that there are 2 to the 56 or about 72 quadrillion different keys. Back in 1977, that meant that nobody, except perhaps the NSA, had enough computing power to brute force all possible keys. But by 1999, a $250,000 computer could try every possible DES key in just 2 days, rendering the cipher insecure. So in 2001, the Advanced Encryption Standard AES was finalized and published. AES is designed to use much bigger keys, 128, 192, or 256 bits in size, making brute force attacks much, much harder. For a 128-bit key, you'd need trillions of years to try every combination, even if you used every single computer on the planet today. So you'd better get started. AES chops data up into 16-byte blocks and then applies a series of substitutions and permutations based on the key value, plus some other operations to obscure the message. And this process is repeated 10 or more times for each block. You might be wondering why only 10 rounds, or why only 128-bit keys and not 10,000-bit keys? Well, it's a performance trade-off. If it took hours to encrypt and send an email, or minutes to connect to a secure website, people wouldn't use it. AES balances performance and security to provide practical cryptography. Today, AES is used everywhere, from encrypting files on iPhones and transmitting data over Wi-Fi to WPA2, to accessing websites using HTTPS. So far, the cryptographic techniques we've discussed rely on keys that are known by both sender and recipient. The sender encrypts a message using a key, and the recipient decrypts it using the same key. In the old days, keys would be shared by voice or physically. For example, the Germans distributed code books with daily settings for their Enigma machines. But this strategy could never work in the internet era. Imagine having to crack open a codebook to connect to YouTube. What's needed is a way for a server to send a secret key over the public internet to a user wishing to connect securely. It seems like that wouldn't be secure, because if the key is sent in the open and intercepted by a hacker, couldn't they use that to decrypt all communication between the two? The solution is key exchange, an algorithm that lets two computers agree on a key without ever sending one. We can do this with one-way functions, mathematical operations that are very easy to do in one direction, but hard to reverse. To show you how one-way functions work, let's use paint colors as an analogy. It's easy to mix paint colors together, but it's not so easy to figure out the constituent colors that we use to make a mixed paint color. You'd have to test a lot of possibilities to figure it out. In this metaphor, our secret key is a unique shade of paint. First, there's a public paint color that everyone can see. Then John and I each pick a secret paint color. To exchange keys, I mix my secret paint color with the public paint color. Then I send that mixed color to John by any means, mail, carrier pigeon, whatever. John does the same, mixing his secret paint color with the public color, then sending that to me. When I receive John's color, I simply add my private color to create a blend of all three paints. John does the same with my mixed color, and voila, we both end up with the same paint color. We can use this as a shared secret, even though we never sent each other our individual secret colors. A snooping outside observer would know partial information, but they'd find it very difficult to figure out our shared secret color. Of course, sending and mixing paint colors isn't going to work well for transmitting computer data, but luckily mathematical one-way functions are perfect. And this is what Diffie-Hellman key exchange uses. In Diffie-Hellman, the one-way function is modular exponentiation. This means taking one number, the base, to the power of another number, the exponent, and taking the remainder when divided by a third number, the modulus. So for example, if we wanted to calculate 3 to the 5th power modulo 31, we would calculate 3 to the 5th, which is 243, and then take the remainder when divided by 31, which is 26. The hard part is figuring out the exponent given only the result and the base. If I tell you I raised 3 to some secret number modulo 31 and got 7 as the remainder, you'd have to test a lot of exponents to know which one I picked. If we make these numbers big, say hundreds of digits long, then finding the secret exponent is nearly impossible. Now let's talk about how Diffie-Hellman uses modular exponentiation to calculate a shared key. First, there's a set of public values, the base and the modulus, that, like our public paint color, everyone gets to know, even the bad guys. To send the message securely to John, I would pick a secret exponent, x. Then I'd calculate b to the power of x modulo m.
Right.
I send this big number over to John.
The math of
John
it
does the same.
when
It
we
means secret
do
exponent.
the full unit on it. Let's see, is this one worth our time or questions worth our time? I would say if you're studying on your own, watch the short YouTube videos on it. And we're gonna do a couple of questions from the practice tests. What's up? That's sort of the point, is you can't, you can't unmix them without knowing what one of the things is. It is sort of like a magic trick. You kind of just have to trust that it happens. From our standpoint as users, as far as getting points on the test, you just know that it is asymmetric, 2 keys, public, what have you. All right, what's up? Yeah, it's beyond me. I'll be honest. The actual math of it is beyond me. Okay, so the documents we're going to use are all 3 practice tests here and the answers as needed, the detailed answers that explain everything, which also a great study tool. All right, so let's take a look at some questions. Okay, which of the following best describes the role? Okay, we saw this one last time. The Internet Engineering Task Force is just the group that gets together and agrees upon standards and protocols for the internet. We talked about this very early on when we talked about the internet. We probably said it for like 1 second, but there might be a question about that. Okay, in public key cryptography, the sender uses the recipient's public key to encrypt a message. Which of the following is needed to decrypt the message? the recipient's private key is how it's decrypted. Okay, that it's kind of sort of inherent in the phrase. Okay, to decrypt, it needs to be private, and the person who needs to decrypt it is the recipient. Okay, public key, asymmetric, multi-key, that sort of thing. Okay, next one. Which of the following is an example of symmetric encryption? Okay, Evie buys a lock that operates two different codes. When the first code is entered, slot opens, allows the message to be put in the box. When the second code is entered, the door opens, the door to the box opens. Evie gives the first code to a friend. Okay, automatically, the idea that there are two different codes should tell you that it's not symmetric encryption. Okay, Finn and Gwen develop a system that maps each letter of the alphabet to a unique symbol using a secret key. Finn uses the key to write a message to Gwen where each letter is replaced with the corresponding symbol. Gwen uses the key to map each symbol back to its original letter. That is symmetric encryption. The same uses the key, the same key, to descramble as was used to scramble. Okay, other things just to look. Hannah writes a message to send to Isabel and hides the message under the rock of the soccer field. Location of the rock, only Isabel. Hiding a message is not encryption. Okay, Juan writes a message to Kelly and slides it through a slot in Kelly's locker. Juan knows that Kelly is not shared. Okay, this is sort of a similar any analogy where one person can put a message in and they'll say like mailbox or lockbox or locker, something that's implied to be secure. Any situation where somebody can put a message into that container, but only one person can get it out, is the essence of asymmetric public key, two-key encryption. So the answer to this one is using the same symbol or the same key twice. Okay, an internet user needs to send private data to another user. Which of the following is the most secure when transmitting private data? Okay, certifying that it's certifying the data with a Creative Commons license before sending it. This is a ridiculous, well, I mean, I guess it's not ridiculous. The Creative Commons is a way of securing or publishing some material that you want to be copywritten, but it has nothing to do with encryption. It has to do with intellectual property. Okay, copyright, not trademark or patent, but that type of thing. Okay, sending the data using a high bandwidth connection, that has nothing to do with security. Sending the data using public key encryption. There you go, public key encryption. That's the answer. Or sending the data using redundant routing. This is another example of them giving you answers that are about other topics from the year. Okay, hopefully you remember about routing, how the internet is a distributed network, so that even if one area goes, breaks or a tree falls on the router, there is still a path there's still multiple paths for a message to get from sender to receiver. That has nothing to do with encryption. Okay, which of the following best explains how certificate authority is used in protecting data? Okay, certificate authority certifies the safety of a particular website so that users know that it does not contain any viruses, has nothing to do with viruses. Okay, certificate authority issues passwords. They do not issue passwords. Certificate authority maintains a secure database that maps all web domains, domain names to IP addresses of servers where they're hosted. I don't think that's it. A certificate authority verifies the authenticity of encryption keys used in secure communications. Yes, it keeps track of the public keys. Okay, so you're not being scammed on what somebody's public key is. Let's double check. This is from the middle test, which is the 2020, where are we? Yeah, question number 40 from 2020. Oh, there we go. Already was there. 40. Question 40. Okay. The certificate authorities are entities that issue digital certificates, which are used to certify the ownership of public keys. Okay, so that's right. Okay, which of the following best explains how IP addresses are signed? Okay, this is from the internet unit. This is not about encryption, but we can still learn from it. As a new device is connected to the internet, it is assigned an IP address to enable communication as a on the network. Yes, every device has its own IP address, its own internet protocol address. It gets it instantly. It is you've probably seen it or had to deal with it somewhere if you've ever connected a router or Wi-Fi printer or something like that. It's the 4 different numbers separated by decimals, dots, called dotted decimal. It probably looks like something 157.1.1.42 or something like that. Every device has its own unique IP address. It gets it instantly. Okay, other incorrect answers. IP addresses are assigned only to servers that host websites. Nope. New devices are connected to the internet without an IP address, but are eventually assigned an IP address once they can be verified. Nope, it's instant, not eventually. And new devices are connected to the internet without an IP address. IP addresses are assigned only for encrypted communications. Nope, unrelated. Okay, the transmission control protocol and internet protocol are used in internet communication. Which of the following best describes the purpose of these protocols? Okay, TCP is the packet system and transmission control protocol, and IP, internet protocol, is the addressing system. Okay, hopefully you remember the phrase or are familiar. IP address is the addressing system, and you just need to know TCP is the packet system. The cool packets, I don't know. Which of the following best describes the purpose of these protocols? Okay, this is not about encryption, but again, we can learn from it. Okay, what is the purpose? To ensure the communication between devices on the internet are above minimum transmission speed. Not really. I mean, no, it has nothing to do with transmission speed. To ensure, what's up? The question about IP addresses. Every device gets its own IP address right away. Has nothing to do with eventually or once it's encrypted, or every single cell phone, every single, digital thermostat, everything that is Wi-Fi, everything that's internet has its own address. Okay, what is the purpose? To ensure communications are above a minimum transmission speed. It has nothing to do with that. To ensure private data is inaccessible to unauthorized, that's encryption, has nothing to do with the internet. Well, the physical internet. To establish a common standard for sending messages between devices on the internet. There you go. These are protocols. These are public shared protocols, standards for making transmissions work. Okay. Another wrong answer. To validate the ownership of encryption keys used on the internet. No. Okay. These are part of the standards that are public, and they make the internet work as is. Nothing to do with encryption, nothing to do with compression, just reliability and redundancy and like it actually working. Okay, the owner of an ebook published an ebook with a no rights reserved Creative Commons license. Which of the following best explains the consequences of publishing a book with a type of license? Okay, again, this is Creative Commons, nothing to do with encryption, but the contents of the ebook will be encrypted and can only be nothing to do with that. Individuals can freely distribute or use the contents of the ebook without obtaining permissions, additional permissions for the author. No rights reserved Creative Commons license. That's what that is. Okay, other wrong answers. Individuals may be legally prevented from sharing. Nope. And individuals may be legally prevented from using excerpts. Also no. Okay, same question. Which of the following best explains how devices and information can be susceptible to unauthorized attacks if weak passwords are used? Okay, we didn't talk about this part of the vocab. Okay, the ways the bad guys get you, the bad people get you. That sounds so much worse. Bad guys is just so generic. Phishing, you should know. It's the sending an email, trying to trick you into clicking on something or going somewhere. Keylogging is some sort of malware that is either installed on your computer or you accidentally install it on your computer that keeps track of every keystroke, every letter you type. And if somebody has access to that, they can probably pretty easily figure out your passwords as a way of breaking in. Malware, any software that is designed for ill intent, could be keylogging, could be just, well, I mean, anything. Keylogging would be a type of malware. Rogue access point is a wireless connection to a network. I guess it doesn't really have to be wireless. I suppose you could plug in a network cable into a router and do your rogue actions. But that is one way to break into a secure network, is actually getting into a computer that's on the network. Okay, so explains how devices and information can be susceptible to unauthorized access if weak passwords are used. There are many ways that information can be susceptible to unauthorized access, but this question is about weak passwords. Okay, unauthorized individuals can deny service to a computer system by overwhelming the system with login attempts. Okay, this is another thing that might be the correct answer. They might ask a question about DDoS attacks. Acknowledge receipts. DDoS attacks, or distributed denial of service, is when the bad people use bots to request or try to load essentially a website, millions of bots trying to load the same website at the same time, crashes it. Okay, it's about overwhelming the target. It is a way of hacking, of hurting somebody else or some organization that doesn't require any sort of access to the network. Okay, a DDoS attack. That might be one of the correct answers for one of the questions. It's not the correct answer for this one. Okay, weak passwords. Unauthorized individuals can exploit vulnerabilities in compression algorithms to determine a user's password. Compression has nothing to do with security. They are both transformations, but compression is for making files smaller for the sake of storage and transmission. Encryption is about making data secret. They both change the initial form, but for different reasons. They are probably used in conjunction, but it's irrelevant. They have different purposes. Okay, unauthorized individuals can exploit vulnerabilities in encryption algorithms to determine a user's password from their encryption key. No. Okay, weak passwords don't require encryption or decryption. It's about getting the victim's password and just logging in. Okay, last one, hopefully it's right. Unauthorized individuals can use data mining and other techniques to guess a user's password. Okay, weak passwords are susceptible to an educated guess. More passwords. Which of the following statement about the internet is true? The internet is a computer network that uses proprietary communication protocols. No, proprietary means private, owned by a business, owned for the sake of selling. It is not. The internet is not proprietary. It is public. It is open. All of the standards are known. Any company or individual can make something that works on the internet. Okay, nobody is in charge of it. No company is in charge of controlling it. There's, of course, ISPs and hardware, and they kind of have control, but the actual protocols are not proprietary. Okay, what else could be true about the internet? This is such a vague question. The internet is designed to scale to support an increasing number of users. Yes, it is designed to get bigger, and it actually gets better as it gets bigger. The more routers that are attached to the internet, the better the internet gets. Slightly, okay? The internet requires all communication. Nope, all communication doesn't need to be encrypted. They'll let you send private stuff if you want. And the internet uses centralized system to determine how packets are routed. No, it is decentralized. Okay, it is a spread out web network that, oh wait, is that where the web comes from? Am I like, the network looks like a web. Wow. I'm either a genius or just like way slow. Maybe that was obvious to everyone. Never mind. Just self-reporting. So the internet is not centralized. It is decentralized. Okay. The network is designed so that if one of the wires or the router breaks, it can still work. Okay. Decentralized. Also nothing to do with encryption. Okay, which of the following statement is true about the use of public key encryption when transmitting messages? Okay, public key. Public key encryption enables parties to initiate secure communication through an open medium such as the internet in which there might be eavesdropping. There you go. I mean, that is a, like, if you were trying to describe public key encryption in maybe 3 sentences, this would be one of them. Go for it. Public, okay, wrong answers, but just to double check, they're not more right and possibly misreading. So another just sort of generic test taking tip is, even if this is clearly the correct answer, always read all of them, because if you come up with another one that also feels correct, perhaps you misread the question and it said like what is not true or something like that. Just a tip for those of you who don't already do that. Okay, possible or likely wrong answers. Public key encryption is not considered a secure method of communication because the public key can be intercepted. No, just no. Public key encryption only allows the encryption of documents containing text. Documents containing audio and video must use different encryption methods. No, all media, all text, video, audio. Is that it? I guess that's it. Any sort of digital anything can be encrypted. There you go. I don't know what else I was going to say. It can be encrypted. Okay. Public key encryption uses a single key that should be kept secure and is used for both encryption and decryption. Nope, that's private key or symmetrical or single key. No, it is not a single key. Public key is 2 keys. One of them public and one of them private. Great question. Okay, which of the following exemplifies the use of key logging to gain access to a computer system? Okay, user unintentionally installs a program on the computer that records all the user's input and forwards it to another computer. A few weeks later, someone else is able to access the user's computer using the recorded data. That sounds like the correct answer. Let's read the other ones that are probably wrong. The user has a very common password for an online banking account. Someone else guesses the password after a few attempts and gains access. This is an issue, but it's not key logging. A user logs into an unsecure website. Someone else is able to view the unencrypted login information as it is transmitted over the internet. The user has the same username and password for multiple accounts. So this has nothing to do with key logging. And the user receives an email that claims to be, okay, this is phishing. Okay, not related. Okay, which of the following best explains how symmetric encryption algorithms are typically used? Okay, symmetric is same key for both people, same on both sides. They didn't use the word symmetric on accident. Symmetric encryption uses a single key that should be kept secret. The same key is used for both encryption and decryption data. That's like 4 or 5 answers that were letter A, but unrelated. There you go. Same key is used for both encryption and decryption. Symmetric. Okay, likely wrong answer. Symmetric encryption uses a single key that should be made public. No. Okay, symmetric encryption uses 2 keys that should be kept secret. No, it's a single key. Symmetric encryption uses 2 keys. Again, one symmetric is 1 key. Same key both sides. So what symmetric means. And I think that's it for encryption questions. Let's see if there's any other multi-factor authentication. They didn't have a question about it, but you should know it's like when you're logging into a website or some other app or account, and after you type in username and password, they then send you a text message with a number, and you then have to type in that number as a way of making sure you at least are the person that's holding the phone of the person that's trying to log in. Hopefully, actually the person. But it's another layer. It's not perfect, of course, if the bad person has the phone. That is a flaw, but it at least handles most of the issues with somebody stealing a password. We did these. Personal identifiable information is anything that, name, name, age, phone number, anything that is information about the person. Community innovation. I mean, that's a very generalized topic. And computer virus scanning software. I mean, it's antivirus. It's exactly what it sounds like. Okay, does anybody have any other questions about encryption? What's up? That's fine. Yeah. I mean, we did a couple of those for they are a difficult category of questions. I would say the best thing to do for any of the programming questions is get out pencil and paper and try to follow along. Worst case scenario is you spend time on it and have to actually work out what the result of the variable is or something like that. That's about as best as you can do. Okay. I mean, I'm happy to do a few of them just randomly. I mean, they do stack the end of standardized tests tend to be more complex towards the end, although not necessarily. There you go. You can use that tidbit. Okay, so here's a basic turtle question. Robot is the triangle that's pointy that way, and the goal is to which of the following code segments would make the robot which of the following code segments will move the robot to the gray square? So it is, hold on, move times. Okay, so think about, like, try to interpret what they want. They want move forward twice, turn left once, move forward 3 times. Now, the problem is that you obviously have twice, you want to move forward, but then 3 times you want to move forward. So it's probably going to be procedure, move forward, move X times. Procedure, move times twice. Hold on. Then repeat X times. Move forward, repeat X times, rotate right. Okay, so we only have right turns. There's one insight. So it's going to be a triple right. So 3 times you want to rotate right. So the middle one needs to be one of the 3s. And then we want to move forward twice. But why is it in a loop? I mean, it should be 2, 3, 3. Yeah, I think so, but it's weird. Pseudocode is a little weird the way that it's written out in these blocks. It looks a lot like their loop situation. Let's see here. This is from the first test, question 21, which this is the first test. 2018 practice test. These are the questions. This is 2018. This is 2020. So 2018, question 21. What? That's not right. That's not the right question. Oh, it's because I opened the wrong one. What is this it? Yeah, 2018. There we go. Okay, 2018, question 21. Sure. Huh. Question 21. Why don't I just go to it? Question 21. Come on, B. Yes. Okay. So yes, it is just straightforward finding the path. Wait, that's not what we're looking for. We're looking for some programming ones. Let's go down, see if we do have more complex ones at the end. And okay, here's one. I think there was a one up above that was the same essentially. Okay, the following spinner used in a game. The region labeled blue represents a quarter of the spinner. The regions orange and purple are equal size. So a half, a 3/4, so they're 3/8. I don't know. That's not super critical to be able to do that math. Okay, which of the following code segments can be used to simulate the behavior of the spinner? So there's 2 of them. Is that what it said? It said select 2. Jeez. Okay. They have a bunch of what? Okay. Yeah, those are obviously tougher. Okay, so first, looking at the differences, they're both if-else statements. These second ones are starting out with a random 1 to 4, which is the odds of it being blue. But okay, so if random 1 to 4 is 1, that means it's blue, which is random between 1 and 4. In this case, is going to come out 1, 2, 3, or 4. So a 25% chance that it's blue. But if it's not, then random 1 to 2, meaning 50% chance, if that's 1, orange, otherwise purple. This seems to be correct because it is the if else, it's only going to run one of them. And if it gets to the else, that means it's not blue. So that means if it's not blue, it's a 50% chance of orange and purple. So this satisfies this. I do believe A is correct. Okay, B, if random 1 to 4 is greater than 1, that is not the odds of it being blue. That's a 75% chance of displaying blue, which is not the case. Okay, random 1 to 4 greater than 1 means, is this random number 2, 3, or 4, which is a 3 out of 4 chance. Okay, spin random 1 to 4. If spin equals 1, display blue, which is actually the same over here. Now, it's using the same random. So spin is declared up here, and it's saying if spin is 2, display orange, otherwise display purple. Spin being 2 is also 25%. Okay, the odds of it being any one of the numbers, 1, 2, 3, or 4, is 25%. So spin equals 2 is 25% of orange, which is not the case. And this one is the same, except it's recalculating or re-randomizing spin to a 50%. So the answers are A and D on this one. And just working through it is really the only way to do it. Okay, so the following code segment is intended to remove all duplicate elements from my list. The procedure does not work as intended. Okay, which of the following contents of my list will produce not, or which of the following lists won't work? Or which of the following lists break the situation? Okay, so J is however many items. Repeat until J equals 1. Okay, if the item that we're looking at is equal to the one before it, okay, so if one of the items we're looking at, which, okay, so here is a thing you need to know, that in pseudocode in this class, and I'm sure well, it technically doesn't matter for this one because we're just using made up variables, but they will tell you that the first element in a list is index 1, which is the opposite of what we've learned this entire year, where the first element is index 0. But having the first element index 1 means that the last element's index is dot length. Okay, if there are 6 items here, the first one is index 1, the last one is index 6, rather than being 0 to 5. Okay, so we're going to repeat until this variable is, okay, so let's just go ahead and start. J is 6. Okay, because all of these lists have 6 elements. Okay, repeat until J is 1. If my list J, which is the last element, is the same as the one before it, remove the last one, and J goes down by 1. Okay, fine. Now, J is the 5th one. If 5 is the same as the one before it, remove it, but it's not, so J still goes down by 1. And now we're looking at the 4th one. If the 4th one, which is now my list index J, is the same as my list index J minus 1, which we haven't done a lot of this inside of the brackets, index math. But if this third time around, index J is this index, that means index J minus 1 is that one. So if they're the same, remove this one, and then J goes down by 1. So we've removed the last one and the third to last one. So now J is here. If J is 20 and this is 10, it's not a remove. J still goes down by 1. And then we check again. It is a match, so we get rid of this one. So the final value for this one is 10, 20, and 10. Okay, that broke it. Now, why did it break it? Because it had similar ones that were not next to each other. The goal is to remove duplicates. But, okay, so this one checked that one, it got rid of it. This one checked that one, it didn't get rid of it. This one checked that one, it got rid of it. This one checked this one, it doesn't get rid of it. This one checks this one, it does get rid of that one. It still has 2 10s in it because they weren't connected. Okay, this one, 20 gets rid of that one. This one doesn't touch it. This one doesn't touch that one. This one blocks this one, and that one blocks that one. Okay. Exactly. It was just about coming up with a algorithm or an explanation in terms of words, what was causing it to break. So the answers are A and C. Very good. And group of hundreds of digital photos. Oof. Okay. so let's work through this. Following procedures are available for string manipulation. Okay, substring, the name of the string, where it starts and where it ends. Okay, it returns a substring of consecutive characters of whatever the string you're talking about, starting with the character at position start and ending with the character position end. The first character substring of strings consider position 1, for example. The substring of delivery 3, 6 means you keep 3, which is an L, 3, 4, 5, and 6. So you keep 3 and you keep 6 and everything in between. It's important to know how they're using indexes. Okay, concat combines the two strings. We know what that means. And length returns how many items, how many letters in the string. Okay, a programmer wants to create a new string by removing characters in position n of old string. For example, old string is the word best, n is 3, then the new string would be BET because they got rid of the S. Okay, assume that n is something, isn't the first one and it isn't the last one. Okay, so the letter they're always trying to get rid of is something in the middle of the string. Okay, select 2 answers. That which of the following code segments can be used to create the desired output of new string. Okay, so a variable named left gets substring from the original string, starting at 1 and ending right before the letter that they want to keep. A variable right gets everything in the old string from starting right after the letter they want to get rid of and going until the end. That sounds right. And then new string combines left and right. Okay, think about if they want to get rid of a letter in the middle, like the E in create, probably zoom in. This variable left is everything before the E, C and R, and right is everything after the E, A, T, and E, and then you combine the two. That is exactly what's happening. Okay, here left is the old string starting at 1, going to 1 past. Right is a substring starting 1 to the left and going all the way to the end on the right. And then you combine them. This would double and would be in the list twice because it's collecting too much for these left and right subvariables. Okay, new string is a substring from the old string starting at the beginning, going to 1 right before n. And then you combine into new string, which is what we just got, gets, new string, combining substring, the substring, whatever this is, with substring of old string. This is doing the same thing. Okay, it's just reassigning new string, whatever it used to be, which is this, which is the same as this, and it's doing it in one less line of code. And this one is the more complex way of doing this one, so it's also wrong. So this is A and C also. Okay, when in doubt, get out a pencil, paper, and work out an example. Does anybody else have specific categories of questions that they need help with? I'm happy to do some more programming, logic, problem solving, which works well for the algorithm questions as well. Sort of the same thing. This looks programmy. Let's see what happens. Okay, the 2 code segments below are intended to display average of the numbers in the list. Assume that numList contains more than one value. Okay, so they both get a variable sum. Well, first of all, which of the following best describes the 2 code segments? 1 is right, 2 is wrong, 2 is right, 1 is wrong. Both work, but code segment 1 requires more arithmetic operations than 2, and the last one, both are correct, but the second one requires more. Okay, so they both start out with a variable sum at 0. For each number in the list, sum gets sum plus whatever number we're looking at, and then average gets sum divided by however many items This one is averaging the sum every time through the loop. That's not how you get an average. You get an average by adding up all the numbers in the list every time through the list. This running total sum gets whatever it used to be plus the number in the list. So this chunk gives us our total, and the average is sum divided by however many items are in the list. And there you go. So only code segment 2 works. So it can't be these. Okay, code segment 2 displays the correct average. Wait, does it? No. Average sum is the total number plus the number. Then you average. Well, let's try a list. 2, 4, and 6. The average should result as 4. Okay, sum gets sum plus num. So that means our sum is 2, and then average is 2 divided by 3. Average is 2/3. Wait, I think this one might work. Okay, then sum gets sum plus num. So then we're at 4, and average gets 4/3. Then, wait, hold on. The average not is 4. The average now is 6 because it's running total 6. So average is now 6/3 or 2. And then the last one is 6. So we get 12 is our running total. So yeah, this one actually works also because it's not average is not a running total. Only the last calculation is correct. Only the last assignment of average is correct. So they both work actually. Now, as far as who is doing more arithmetic, this one is doing 2 arithmetics every time through the loop. This one is only doing 1 through the loop plus 1 at the end, an extra one. So code segment 1 has more arithmetic. Okay. They both, code segment 1 requires more. Okay, I think it might be C, and it's probably from the first one, number 37. Let's see if it is correct. 37, please be C. Yay! The teacher got it right. They both end up with the correct answer. And you saw how I just ran through it with some pencil. Okay, another one. Procedure smallest is intended to return the least value in the list of number. Lowest, I guess. The procedure does not work as intended. Okay, the same as the question before. Okay, procedure smallest receives the list numbers or receives numbers. Minimum is the first thing in index 1 for each number. If the number we are, wait, hold on, numbers. If number it doesn't assign number, but I guess we're just saying for each number in numbers, meaning this is the same as a for loop where they were like bar I 0 while I is less than however many numbers. It just means the counting variable is number, or the item we're checking is number in the list numbers. Okay, if the item we're checking is less than the minimum, return that number. Otherwise, return the minimum. The problem is that returns end the function. So that means if you ever get to a number, if you're ever checking one that's lower than our running lowest, which is our min is our running lowest, that will end it. So the problem would be if we come to a number that is lower than our, numbers index 1 is our running lowest. So as soon as we find one that's lower, then like it's not increasing, it will break it. Okay. Which of the following values of list will smallest the list not return the intended value? So it's any of them where they're decreasing. I think. If number is less than minimum, return. I think this one breaks it because it decreases, and this one also breaks it. That no, well, for each number. Where does this? Oh, because the for loop doesn't return. Okay. So it will return the incorrect one. Okay. Well, I mean, we could just work through it. Okay. For this one, we're checking minimum is given whatever's the first in the position. So minimum for, if we work through this one, is 10. Okay. For each element in the list. Okay. If number, the one we're checking, is less than our running total, it ends the loop and returns that number. So we check, we've already checked, it's the same, it's not the thing. Okay, second one, it is not, the number we're checking is 20, is not less than our running total. So we go around again. 30 is not less than our running total, and 40 is not less than our running total. So we return whatever minimum is, which is correct. So this one does work. Okay, it's not the one that breaks it. Okay, this one, min is given 20. Then we check the next one, and it is less than minimum. Okay, so that means we return the number we're checking, which is 10, which this one does work correctly. The next one, minimum is 30. Okay, this one already is broken. So correct. No, A is one. Wait, did A return it correctly? Okay. Yeah. So this one, if it's less, return number. I think it's if the last one is lower than the one, if number is less than min, return number. Okay, it has to do if it ever drops. But what? If it ever drops and the one it drops to isn't the lowest. So this one does have a decrease, but the one it decreases to happens to be the lowest. And this one decreases. Does it? Am I broken? This is a tough question. Let's see, is C and D, and it's question 137. I think it's the last one from 2018 is my guess. Yeah. Yes, it is C and D. Okay, the procedure returns the first number it encounters that is less than the first number on the list. Yeah, so as soon as it finds a lower one, it returns the lower one. But if that lower one, that one that it decreased, isn't actually the lowest, it returns the wrong one. Okay, so we had it sort of without much confidence. Okay, yeah, C and D were the correct ones because it decreased to one that wasn't actually the lowest, because it returns whatever number was decreased to. Okay, here's a fun one. 2 different schools maintain data sets about currently enrolled students. No individual student is enrolled in both schools. Each line of data contains information separated by a comma about one student. East High School stores the data in the following format: school name, last name, first name, age, zip code, and number of days absence. West High School stores student ID, first name, last name, age, and days absent. The 2 schools would like to combine their data to make a single set. Which of the following can be done to combine the data? The schools can create a single list of names sorted by last name. The schools can create an average number. Wait, which of the following can be done with combined data? Okay, so we could have a single list of students because sorted by last name, because both sets keep track of last name. Schools can determine average number of days students are absent. Yeah, why not? Schools can determine zip code is represented by most students. No, zip code's only in East High School. And schools can determine student ID of the student with the greatest number of absences. No, the East doesn't keep track of school ID. That actually was a pretty easy question. And just to make sure I can read correctly, let's take a look here. 132. 132. Yes, A and B were the correct answers. That one I think was actually pretty easy. Okay, we did that one. A group of students. A lot of these, like they keep track of this data, and we keep track of the metadata, what information is available. That's just sort of reading and interpreting. It's not that much programming. Okay, let's do this one, and then I think, I don't know, then I think we'll do another one. Okay. In a certain video game, players are awarded bonus points at the end of the level based on the value of the integer variable timer, meaning based on how much time is left in whole seconds. Okay, bonus points are awarded as follows. If timer is less than 30, then 500 a point. 500 timer is less, because you didn't have that much time left. Get 500 points if it's between 30 and 60 inclusive, meaning greater than or equal to 30 and less than or equal to 60, you get 1,000 points. And if it's greater than 60, you get 1,500. Okay, which of the following code segments assigns the correct number of bonus points for all possible values? Select 2. Okay, first one, everyone gets 400. If it's greater than or equal to 30, you get an extra 500. And if it's greater than 60, you get another 500. I think that's correct. Possibly. If bonus starts at a 1,500, if it's greater than or equal to 30, you lose 500 points. That doesn't make any sense. If you're just reading it out in English, it might make more sense. Okay, if timer is greater than 60, you get 1,500. If it's greater than or equal to 30, you get 1,000. This already is broken. Imagine you had 100 seconds left. You should get the biggest bonus. And it has gone to this one, and this one would be true. So your 100 seconds left over should be the top bonus, and you only get 1,000. So that one's wrong. Let's check this one. If timer is greater than 60, you get 1,500. If it's greater than or equal to 30 and less than or equal to 60, 1,000. And if it's less than 3,500, this is explaining it exactly. Just a quick note, being aware, I am surprised they didn't have the same, having this be one of the wrong answers, but with an or. I think that would have been a good question for them. Just knowing when to use and or is good, which is what this one is, I think. Assume a Boolean variable hot gets true, and humid. Okay, assume the Boolean variable hot gets true and humid gets false. Which of the following will display true? Select 2. Okay, if hot, which it is, display hot and humid. Okay, and means they both have to be true. And they both are not true. So yes, the if is true and it gets to display, but since they're both not true, it would still display false because humid is false. Okay, if not humid, which it is, it's not humid, display hot or humid, and or if either is true, it displays true. This one will display true. Okay, if hot or humid, which it is, it's one of those two, it is hot. Display hot. Hot is true. This displays true as well. And if hot and humid, which it's not, so that ends the conditional. So B and C are the correct ones there. Oh man, this is one of the toughest types of questions, and I guess this one will be the last one for today, where they give you a function, a procedure, and they ask you which two lines of code, no, removing which two lines of code will cause the program to work as intended. You have to figure out which lines in this thing are breaking it. And there are two lines that are keeping it from working. I mean, just knowing what we've done so far in this class, I think this is kind of on the limits for a lot of people. But if you take your time, you'll have a better chance. Okay, let's see what it's supposed to do. Following procedure, the parameter age is the age. The procedure is intended to return the name of the age group associated with an age. People under 18 are minors. People who are over 65 are senior citizens, and under 18 is a minor. 65 and over are senior citizens. Everyone else is an adult. Procedure does not work as intended. Okay, so our function age group receives a number, and the whole thing is the function. Our variable result gets assigned the word adult. If it's 65 or over, greater than or equal to 65, result gets senior citizen, return result. Now, the problem with this return statement, we didn't spend a lot with return statements, but we did a little bit. You have to know a return ends the function. So line 8 ends the function with the result of this question. Adult, if they're less than 65, and senior citizen if they're 65 or older. This doesn't work with an age that's supposed to be a minor. So we definitely need to get rid of this return. Line 10, result gets assigned adult, even if it was just assigned senior citizen. So this breaks it also. No, wait, does it? Result gets assigned adult. No, because we would want senior citizen to carry through to the end, and this blocks it from carrying through to the end. So this one also blocks it. So I think 8 and 10. So it's just asking two questions. Okay, it's an adult unless it's over 65, and unless it's still an adult unless it's less than 18, and we return whatever the result is. So it's 8 and 10 are keeping this from working. Either of them is keeping it from working. All right, let's do this one logic one. This is fun. Okay, for each of the questions, incomplete statement below, 2 of the suggested answers. Wait, questions 31. Oh, these are all different. Okay, 2 of the suggested answers are correct. For each of the questions, you must select both. Okay, so this whole unit is the 2-answer situation. Okay, following table shows the value of expression based on inputs 1 and 2. Okay, so if both are true, it's false. If one of the two is true, it's true. If one of the two is true, it's true. If both are false or true. So it's true so long as there are no falses. Okay, which of these explain this? So if it's not input 1, so in other words, if input 1 is false, or not 2, it's true. But is that the case? Okay, this is saying if input 1 is false or input 2 is false, it's true, which is what's happening. It's asking if either are false, it's true, which is the truth. If either are false, the entire thing is true. Okay, so this is correct. Okay, this one is asking if input 1 is false and input 2 is false, it is true. But there are other true situations. So even though this one is true, it could also be true if either. Okay, then it's asking if not input 1 or input 2, it becomes true. Yeah, that's the same thing. It's asking if either are false, it's true, and the inverse. Okay, and I keep saying it's the last, but I do actually like this. Oh, okay. This is a good one about parallel computing in algorithms. Certain computer has 2 identical processors that are able to run in parallel. The following table indicates the amount of time it will take to execute each of the 4 processes on a single processor. Assume that none of the processes is dependent on the other process. This is what we were talking about last time about sequential programming versus parallel programming. Parallel, you can have different processors, different computers, different people do the tasks separately in order to accomplish them faster, where unless each of the tasks requires the result of the previous one, then it can't be done parallel. Okay, so we have 4 processes P, Q, R, and S, and they take 30, 10, 20, and 15 seconds respectively. Which of the following parallel computing solutions would minimize the amount of time to execute all 4 processes? Okay, P and Q are in one processor, and R and S are this on the other one. So that would be 40 seconds on this one and 35 on this one. R and S are 20 and 35. The amount of time it takes is whichever is the slowest combination. Okay, so this is 40 seconds for them, 35 seconds for them. The option A takes 40 seconds to complete. Okay, option B is P and R, which is 50. Okay, P and R is 50, and Q and S are 25, so it takes 50. That one is slower than the first one. Our running best is 40. Okay, P and S is 35, and Q and R is 30. This one takes 35 seconds to run. P and S take 35. That makes it shorter than 40. Okay, P on one and Q, R, and S on the other. So Q, R, and S is 20, 30 is 45 seconds. So the fastest one is putting P and R on one and Q and S on the other. Wait, no, wait. P and S. Yeah, it's this one. P and S on one and Q and R on the other is the fastest. So there you go. You saw some parallel computing situation. That was a lot of words. Okay, code segment is intended to transform the list of utensils so that the last element of the list is moved to the beginning of the list. Okay, that's the only job of this, is to take whatever is the last item and scoot it to the front. Which of the following code segments transforms as intended? Okay, so variable length gets, and we can work it out just with our list of options. So length gets however many items there are. So in this case, it'd be 5. Temp gets whatever is in utensils at index length, which again, they start from the utensils at index length is the last item. It's not length minus 1. So temp gets the last string. You remove the last one and then append to the list whatever's in temp. No, you do need to know append goes to the end of the list. Okay, insert goes to wherever you put it. Okay, this one, length, number of items. This one removes the last item first. If you remove the last item, you can't do anything with it afterwards. So clearly that one breaks it also. Okay, length, number of items. Temp is whatever's in the last position. We remove the last one, good. And then insert, okay, we were keeping track of it in temp. Insert into the list utensils at index 1. This one works. Okay, just to be sure. Okay, number of items. We remove, okay, this one again is removing the one that we want to move before we're doing anything with it. So key takeaways here are knowing the difference between append and insert. And okay, some more keeping track of data and figuring out what it is. Target appears to be on the list more than once. I don't know. That feels like enough for today. Make sure, like, for real, if you are serious about getting a good grade on this, on the test, it's up to you to do the study. Okay, we can talk about stuff as much as we want in class, but just being in class, and even if you got all A's this year because you did the assignments and jumped through the hoops and everything, that's not enough to get 5 out of 5 on the test. You need to go back and review how binary works, how bits work, okay, how different number systems work. Okay, you won't need to, I don't think you'll need to convert to hexadecimal, but you should know what hexadecimal is. Okay, you should know what binary is and how it works. Okay, overflow error, when you're trying to keep a number that's too big for the number of bits. 4 bits only goes up to 15. If you want to keep a number like 17, it will have rolled over and will be the number 2, I think. Actually be the number 1, but irrelevant. Okay, round off error. Again, you have trying to be too precise. That is rounded. Round off error is exactly what it says. Okay, analog. We didn't really talk about this, and I haven't seen a question about it, but still information. Okay, sampling, process of creating digital representation. Okay, lossless and lossy compression. There will be multiple questions about that, and probably at least one about Creative Commons. Okay, internet key issues are everything's a protocol. IP address and internet protocol, same thing. Router, the way that the network is spread out and distributed. Packet, we did that where you send small messages with metadata so that you can reconstruct them and only one of the packets needs to get through. Redundancy is exactly what it sounds like, doing things multiple times to be safe. Fault tolerant is a synonym for redundant in this case. Even if one piece of the internet breaks, it still works. DNS is the system that allows you to use words for websites instead of just IP addresses. They are just servers on the internet that your computer knows to connect to, and they keep track of all the internet IP addresses. You give them the name of a website, they return which address to look at. Digital divide. Okay, this is sort of global impacts, but there might be a question about it. It's the idea that there are people that are on the wrong side of the digital revolution. Usually they like to focus on how rural people don't have broadband access frequently or cell access, and it makes it difficult to do a lot of the things that we take for granted. Or sometimes they will say things like about senior citizens that are less likely to be on, smartphones and more likely to be on the internet. How would they be not discriminated against, but how would their input not be collected, or would be some bias on information collected if whatever group wasn't included in that information? That's a lot of question about bias. There aren't going to be specifically questions about comments or Well, there might be one about documentation. Documentation is the library, is the help source. It is the instructions of how different programming works. In App Lab, it was just the like when you mouse over and it says see examples, that is the App Lab documentation. I won't go into it. Other questions that might be on there, comment, pair programming. Expression, assignment operator, that's just the equals. Okay, these terms would be useful if you're trying to interpret pseudocode, and they're like, such and such is an example of what an assignment operator looks like in pseudocode, which, again, if you're serious about this, taking a look at the pseudocode reference sheet is going to be useful to some extent. They do give you a pseudocode reference page on the test itself, just to be fair, but I think it's here. Come on. Doop. Where is it? There we go. No, is this it? Yeah. Pseudocode reference materials. Okay. Evaluates expression assigned to the variable A. So you would need to know assign and, just general terms. And I think that's where we're going to stop for today. Data bias, crowdsourcing. Yeah, here we go. This is another category that would be useful. Again, but a lot of this is just you're a digital citizen and you know things. So that list, element, index, iteration is just a loop. Infinite loop is when something like the end condition, there will be a question about this, where like which input causes an infinite loop, and it's whatever input would never trigger the end condition. Like if it's a while loop or a for loop that's saying continue this so long as this counting variable is greater than something, and then in the loop it adds one to it as a way of keeping track of things. If the starting number was on the wrong side, I'm not giving a good example, that would never trigger the end condition. That would cause an infinite loop. Traversal is just the loop through a list. And parameter, argument. I don't think they'll ask you a question with the difference between parameter and argument, but argument is just what gets sent to the parameter. Okay, we were using parameter the whole time, which is not incorrect, but technically in the function call, whatever you send to it is the argument, and when it's received is the parameter. Okay, return statements also end functions. We should focus on abstraction. I don't think there are a lot of questions for abstraction. Maybe we'll do it next time. Let's see how many questions are on abstraction. Either way, that's where we're going to end it. Which of the following are ways in which programmers use abstraction? Yeah, we'll talk about abstraction next time. Okay, so that's where we'll end it for today. One more day.